The topic of this lecture is lock-based concurrent data structures. Adding locks to data structure makes the structure thread safe. And how locks are added determine both the correctness and performance of the data structure. First one is concurrent data counter without locks. So this is a counter, and it contains a value field. And there are three functions: init, increment, decrement, and get. So in init function, it initializes the value to 0, and increment function increases the value by 1. Decrement function decreases the value by 1, and get function returns the value. For this data structure to be thread safe, every instruction should be properly protected by the lock. So it has to be updated with a lock. So in the counter data structure, we add a mutex, pthread lock. And then in initialization function init, we set the value to 0 as well as we set the value of the lock as null. Then every update operation on the value should be properly protected by the lock. For example, in increment operation, the operation of increasing the value of the lock is protected by lock and unlock. That is for sure. And that also applies for decrement and get. For decrement, we protect the function of decreasing the value by 1 as lock and unlock. So before we decrease the value, we obtain a lock. And then after we decrease the value, we call unlock. And then there is get function. So get function retrieves the value of the counter. Before we retrieve the value of the counter, we obtain a lock. And we access the value and retrieve the value. And after we are done with retrieve the value, we call unlock. So there is lock and unlock. So one thing you have to notice is the get function does not change the value of the lock, but still it holds an exclusive lock for the retrieving purpose. So later, we are going to deal with the read-write lock, where that type of lock allows multiple readers to proceed at the same time. But here we does not allow that. Even for the read operation, we hold an exclusive lock for that operation. Let's consider the performance of the simple approach. Adding a simple lock successfully avoids the race condition and updating and retrieving the counter value. However, what about the performance? We do simple experiment here. There are a number of threads. Each thread updates a counter value 1 million times. And we've done it in iMac, which has 4 cores, Intel 2.7 GHz i5 CPUs. We measure the time to increase the counter value on the varying number of threads. There are 4 CPU cores. There are 1 thread, 2 threads, 3 threads, and 4 threads. Because there are 4 CPUs in the system, each thread is going to run on the separate CPU. Ideally, so the total execution time should remain the same when we increase the number of threads. However, if you see here, the total execution time increases linearly, almost linearly, as we increase the number of threads. Even though the threads run on its CPU core, they fail to execute in parallel. So, of course, this is because of the lock. Plain lock fails to scale. So a group of researchers has proposed a concept of sloppy counter. And if you apply sloppy counter, then the execution time remains the same even though we increase the number of threads. So even though more work is done, ideally the work should be done in parallel, and the time it takes to complete a task should not increase in perfect scaling protocol. But there is nothing like perfect scaling protocol. So a group of researchers has proposed the concept of slope counter. Slope counter consists of one global counter and a number of local counters. One global counter and a number of local counters. Slope counter defines local counter for each CPU core. So if there are 4 CPUs, then there are 4 local counters and 1 global counters. And there are also locks. So 1 for each local counter and 1 for global counter. Now let's consider an example with 4 CPUs. Then there's going to be 4 local counters for each CPU core, and then there's 1 global counter. Basic idea of slope counting is quite straightforward. When a thread needs to update the counter, decrease or increase it, it updates local counter. So since it updates local counter, there is no contention. And the value of the local counter is periodically folded to the global counter. It is updated as follows. Local counter is transferred to the global counter as follows. It acquires the global lock and increased the value of the global counter by the local counter's value. And then local counter is reset to 0. And then we have to, of course, release the global lock. This is how we update the global counter. How often the local to global transfer occurs is determined by the threshold value S. So as the value of S means slopiness, and as S gets smaller, the local counter is transferred to global counter more frequently. So if S gets smaller, then the slope counter becomes non-scalable. If the S gets bigger, then the scale counter becomes more scalable, but the global value can be further off from the actual counter state. Let me provide an example. There are 4 threads and there are 4 counters. So this is thread 1, thread 2, thread 3, and thread 4. Then the threshold value of slopiness is set to 5. It means that if the counter value reaches 5, then it is folded to the global counter. So each thread updates local counter, and local counter is labeled as L1 to L4. So this is local counter 1, this is local counter 2, local counter 3, and local counter 4. So this is how we update it. At time 0, all values were 0, and global counter is 0. At time 1, thread L3 and L4 has increased to 1. And then it gets increased at, let's look at the timeline at time 6. Here, the local counter L1 becomes 5. It increases by 1. At this point, the slope counter folds the value 5 to the global counter, and global counter becomes 5 from 0, and then local counter L1 is become 0 as a result of reflecting its value to the global counter. At the next step, local counter of L4 becomes 5, and then immediately after it becomes 5, the value of 5 becomes 0, and the value is reflected to 10. So if you look at the real correct value of the global counter. Here it's 1, but actually this is 2 because there's 1 and there's 1. And the reference counter or counter value at time t2 is in total 4 because L1 is 1, L3 is 2, L4 is 1. Total is 4. And then here the actual counter value is going to be 6. And then here the actual value of the counters is going to be 8. And then at next time the actual counter value is going to be 11, right? So this is true count. So as you can see, the value of the global counter and the actual summation of the local counters is not the same. This is the same, but in most of the time it is different, right? So the role of slopiness is to achieve the scale at the cost of correctness or accuracy of the counter. So this graph shows the performance and slopiness for the counter. So if the value of S, the slopiness, is small, then performance is poor, but the global counter is going to be quite accurate. However, if S is large, then performance is going to be excellent, but global counter may not properly reflect the real situation. So this is time it takes to run 1 million count when the slopiness value of S corresponds to 1 when we vary the value of slopiness count S from 1 to 10,024. This is the implementation of the slopy counter. If you look at the code, there is a counter structure. We have to first define the counter structure. It has global counter and it has an array of local counters, and it corresponds to the number of CPUs. And for global counter, there is a lock to protect it, and also for each local counter there is an array of local counter locks. And then there is slopiness value threshold S, and it represents the update frequency. So init function initializes all the counters and the locks. So it sets the global value counter to 0, and also it sets the local counters also 0, and also it resets, initialize the global lock, and also it initializes the local lock. Okay. And let's look at the update. Counter update is simple. It first identifies the threads, and then it locks the associated lock for the local counter, and then it increases the local counter by a certain amount specified in the parameter. And then if the value of the local counter is greater than a certain threshold value, then it's time to fold the local counter value to the global counter. Then it acquires the global lock and then reflects the value of the local counter to the global counter. And then after updating the global counter, it releases the lock. And then it resets the value of the local counter to 0. And then once all this is done, then it releases the locks on the local counter. So that's update. Okay. Then get a value of the local counter is pretty simple. Not local counter. Get the value of the counter is pretty simple. It acquires a lock on the global counter, and then reads the global counter, and then it releases the lock on the global counter. That is how we retrieve the value of the global counter in sloppy counter. Now we examine the concurrent linked list. The linked list is protected by the lock, and the list is initialized with the lock. When performing an insert or delete operation, the application first has to lock the data structure. So there is a node, and there's key, and there is list. So this is node, and linked list has a head pointer, and it has a lock. And then this is head pointer, and so this is the concurrent linked list. So it consists of a list and the lock. It's pretty simple, huh? So in list init operation, it initialized head pointer with null and initialized lock as well. So there are two functions here. There is list insert and another is list lookup. In both cases, it first obtains a lock. In list operation, there is lock. This is head. And in list operation, it accepts two parameters. First one is pointer to the list, and second one is the key. In insert operation, it first locks the list, and then it creates a node by allocating a memory chunk and set the key value of it. So it says the key, and then after allocating a new node and initializing it with a key, then it sets the pointer of the newly created node points to the first node in the list. And then it cut this pointer and let the head pointer point to the just created and newly created node. So this is insert. In the course of doing this, you have to protect the list from the concurrent access. So at the beginning of the list insert operation, it acquires a lock, and once it's over, it releases the lock. Okay, that's very plain, simple operation. In the course of executing this sequence of instructions, it is possible that memory allocation may fail. Okay, and new node is allocated null pointer. In that case, you have to perform some exception handling. So you have to consider the case where memory allocation fails, and in that case, before returning from the list insert operation, you should unlock the lock. And in the list lookup operation, you have to first lock the entire list and then do search. So the objective of list lookup operation is to scan the list and find the node that has the key. So it locks the list, and then from the beginning of the list, it scans and checks if the value of the current node is same as the key value. And then once you find it, then it returns. Let me explain more on the insert operation. At the beginning of the insert operation, the code acquires a lock upon entry, and then the code releases a lock upon exit. So let's go back to the code. Here, in list on the insert operation, the code acquires a lock at the beginning of the code and releases the lock at the end of the insert operation. So all these set of instructions are protected by the lock. However, if you look at the code in detail, then actual critical section means that the piece of code that accesses the shared data structure is these two instructions, 1 and 2. So you do not have to protect all these sequence of instructions. Instead, you can remove this lock instruction to here, like this. Okay. So you lock the data structure just before you performing an actual insert operation. And then you unlock the code right after you insert an operation. So the number of code lines that is protected by critical section or lock is has become a substantial smaller. This is good for the exception handling and good for the performance. Okay. So far, the concurrent linked list is protected by a single lock. So even though there are thousands of nodes in the linked list, and even though there are multiple threads and they want to access different parts of the linked list, only one thread at a time can be accessed the entire linked list. So that is not scalable. To make the linked list scalable, there is a technique called hand-over-hand locking. In this approach, every node has its own lock. So whenever an application traverses the list, it first grabs the next node's lock and then releases the current node's lock. So in this approach, the application only locks the current node it is accessing. It increases the number of threads that can access the list concurrently substantially. So it enables a high degree of concurrency in list operations. However, in practice, the overhead of acquiring and releasing locks for each node of list can be prohibitive. And there's another data structure called concurrent queue. The difference between the linked list and queue is the location where the modification happens. In the queue, and the concurrent queue, there is a head and a tail. So this is head and tail, and there are two locks, one for the head of the queue and the other for the tail of the queue. So the goal of these two locks is to enable concurrency in in-queue and dequeue operation. And also you have to add dummy node in the initialization code. This is to enable the separation of head and tail operation because we have to differentiate the head and a tail. Data structure for concurrent queue. There is a node. And this is key and this is pointer. And then this is queue data structure. And it has two pointers, one is head and the other is tail. And there are two locks defined for the queue and tail respectively. One is head lock and the other is tail lock. In initializing queue data structure, you first have to allocate the dummy node and whose next pointer is null. And then head pointer and tail pointer should point to the temp. And then you have to initialize the tail lock and head lock as well. Let's examine the code for in-queue and dequeue operation. First one is in-queue function. Let's say there are linked list. And this one is pointed by head. And this one is pointed by tail. Then in queue operation, you first create a node and set the value of the node as key. And then first, you set the next pointer of the tail points to here. Okay, first. And then you update the tail pointer to points to the last node that has been just created. So this is in-queue operation. Next operation we are going to explain is dequeue operation. In dequeue operation, it returns the value of the head node and then move the head node to the next node. Let's assume that this is head, and then there is some nodes, and this is tail. This is tail. The value of head node is 9. And then, as a result of executing head dequeue operation, it moves the head pointer to the next. And then it returns the value 9, and then it deallocates the memory chunk that has been occupied by the head node. So this is the operation of dequeue. To avoid any race condition, it first protects the queue with lock, and then it unlocks. So this is the dequeue operation. The next data structure is concurrent hash table. Hash table does not resize. And then it built using the concurrent list. So it uses a lock per hash bucket, and each of which is represented by the list. So this is hash table. And then each entry in the hash table is a list. It's concurrent list. It looks like this. So this is concurrent hash table, and each element has its own separate locks for the scalability. So this is hash table data structure. It's a lists array, and the amount of the number of elements in the array is defined as such as buckets, and then currently is defined as 101. And in the initialization of function, it initializes the individual linked list in the hash table. And the hash insert is the same as the insert operation on a single linked list. So it calls list insert operation. And hash lookup is the same. It is a list lookup for a specific hash buckets. So it's basically list operation. Let's look at the performance of concurrent hash table. Let's change the number of concurrent updates from 10,000 and 50,000 for each 4 threads. And if we use simple concurrent list, then the time to update the linked list linearly increases with the number of insert operations. But however, if we use concurrent hash table, then the insert operation becomes a lot more scalable, and simple concurrent hash table scales magnificently. So in this lecture, we have dealt with a number of concurrent data structure. They are slope counter, concurrent list, concurrent queue, and concurrent hash table.